This lesson is on trig integrals, and in order to work through this lesson, really this slide is key. It is really key. Knowing this, we probably all are familiar with the sine squared plus cosine squared thing. I don't think that's a problem. And the versions that we see it in. This one perhaps we haven't looked at it this way before, though it's used like this a lot. This is a double angle formula for cosine, and hopefully we recognize that's one of the versions of the double angle formula for cosine. And so what they do is they solve for sine squared. We're going to be able to take sine squareds because integrating sine squared in many cases is not going to work. So we're going to be able to take sine squared out and replace it with this expression. Same thing, the double angle formula for cosine. This is another version of it, the one that just has cosine in it. And we are also going to be able to take cosine squared out and replace it with this. This, 1 minus cosine 2x over 2, 1 plus cosine 2x over 2, are things that really you need to have committed to memory. Because what that is going to allow us to do, it's going to allow us to take care of integrating a cosine squared in situations where we can't do U substitution or something. So these formulas are going to become very important. We do need to memorize those. The formulas over here are basically a version of our addition and subtraction formulas. They are also pretty important because if we are multiplying, and we'll do a problem like this today, if we're multiplying sine and cosine together with different, like A and B, different angle measures, then if we can split them like this, they will be much easier to integrate. So these formulas are used to make the integration possible. Today we're just looking at this form, sine and cosine, sine to some power, cosine to some power. So with that said, those trig formulas are going to be pretty important. The other thing, and this is just a reiteration of the ones that I had up there. They're not different, they're the same. I'm just using those again. So here is these guidelines that some mathematician came up with after doing tons of these integrals. They came up with a technique, just much like the LIATE that we used the other day. It's just it was created by pattern, mathematicians noticing patterns, just as a help. This little box right here is a huge help. And again, it was created by noticing patterns. It's not like a rule, it's just helpful if you can remember it. If you can't remember it, you might be messing with them quite a bit. So let's talk about what the guidelines are. If the power of cosine is odd and positive, and we're really, for our purposes, we're going to be just dealing with positive exponents for sine and cosine. Yes, it's possible to do negative exponents. We're just not going to deal with that in this lesson. So we're going to look at cosine being odd and positive. What we do is we reserve or save one of the cosines out and convert the remaining factors to sine. Now that might sound crazy to you right now, but I'll show you in just a moment. We save a cosine out and convert the rest to sine, like using Pythag. The second helpful guideline is if sine is odd and positive. Notice if one of them is odd and positive, we want to save one of those out. Save one sine factor and convert the remaining to cosine. So that's kind of the same concept, just given a different function. Okay, that's what we're going to do if one of them is odd and one of them is even. Now, if both of them are even, if both sine and cosine are even, we have a little bit of a different strategy. So you see how, again, somebody figured this out after doing probably hundreds of integrals with trig. They figured out, oh wait, now when I did this, this was better. If both of them are even and non-negative, which again we're not going to be dealing with negative ones, then we're going to replace the cosine squareds and the sine squareds with this formula. So I guess we just give up, convert. Just don't worry about saving one of the ones out, just convert them to these. Okay, and that is the structure that we're going to be, we have, I think, four problems to work. I've tried to pick out a variety of different kinds. Of course, I can't do one of every single thing, but I tried to pick out some big types. All right, we okay so far? Okay, let's move to the examples. All right, bless you. So let's look at our first one. Move that out. Our first one is has just cosine by itself. That's okay. All right, so cosine is odd. So we're going to follow that first, guideline, suggestion, and we're going to save one of them out. So I'm going to rewrite it. It's going to be integral of cosine of 5x and then cosine squared of 5x dx. Okay, it's just a rewrite, the very first one. Now what the guidelines say is we save one out and then we turn what's left into, if it's cosine squared, we turn it into sine squared. So we would use our Pythag and turn that into 1 minus sine squared. Okay, so that's going to be cosine 5x, and then we're going to turn cosine squared into 1 minus sine squared 5x. Okay. At this point, one technique, and this is the technique that I tend to like, if I make u sine x, we know the derivative of sine x is cosine x. That's going to take care of this. And this is going to go away as part of the derivative, and I'm going to be left with 1 minus u squared. Okay, I would do a u substitution here. And so we would make u equal to sine 5x. So du, and we're going to have to remember how to do a chain because we have that 5x in there. Du would be 5 cosine 5x dx. I don't really have a 5 in my integrand, so I would divide by 5. So 1/5 du equals cosine 5x dx. So this part, the cosine 5x and the dx, is going to be replaced with the 1/5 du. Okay. So we have 1/5. That part goes away, and then we'll have 1 minus u squared du. Okay. And then we just integrate that as normal. So we'd have 1/5. Integral of 1 would be u. Integral of u squared, 1/3 u cubed plus c. Then I would insert the u back and distribute the 1/5. So we have 1/5. My u was sine 5x. Sine 5x. Minus 1/5 times 1/3. We would have 1/15. Sine cubed 5x plus c. And that is our first trig integral in this form. Okay, so what we did was we used the suggestion. We saved one, because it was odd, we saved one of the cosines out. We turned all the other cosines into sines, and then did u substitution. Okay? We okay so far? All right, the second one. Now the second one, I have a combo. I have cosine that's cubed and sine that's squared. So let's follow what they suggested. Let's save one of the cosines out, and let's turn everything else to sine squared. And I already have a sine squared, so let's save a cosine out. I'll rewrite cosine x, and then I would have a cosine squared x and a sine squared x. Okay, so let's turn that cosine squared x into 1 minus sine squared. Okay, so we have cosine x, and then I have 1 minus sine squared x and sine squared x. Okay. Again, same kind of scenario, that is with the u substitution. If I make sine u, then it's going to take care of my cosine, and it's going to give me 1 minus u squared times u squared, which we would just distribute and do reversal power rule. So let's do that. So let's make u sine x. Du would be cosine x dx. So the cosine x and the dx turn into du, and sine x turns into a u. So I have integral of 1 minus u squared times u squared du. I'm not going too fast, am I? Are we okay? Yeah, I'm going to have to. Yeah, because I really can't integrate it right there. Yes. What is the what? Yeah, we're not to that yet, dear. That's when they're both even. That's down here. I don't need them yet. I will need them. Okay, so let's distribute. So I have u squared minus u to the fourth du. And now let's integrate, just like we would normally. So 1/3 u cubed minus 1/5 u to the fifth plus c. Then we're just going to put our u back in, and we have it. 1/3 sine cubed x minus 1/5 sine to the fifth x plus c. Okay, so those were a couple of examples that used odd powers, and they basically, we reserved one. We reserved one and turned the rest to whatever the other one was, because I hope you can see they're derivatives of each other. And so what we've done is kind of reserved one for the derivative part and allowed us to do u substitution. Okay? All right. The third one is one where they're both squared. They're both even powers. It doesn't have to be squared, just they're even. So we can't really do the whole reserving thing, and that's not going to work for us. So the advice they give us is, if the powers of both sine and cosine are even, use these identities. All right, so what we're going to do is we're going to use the identities on the previous page. Cosine squared is 1 plus cosine 2x over 2. And sine squared is 1 minus cosine 2x over 2. So we're going to use those. We're going to immediately rewrite. So the sine squared, now let's talk about the 3. You know, we're going into a formula that has 2x. So what do you think the 3 is going to do to the formula? It's going to cause it to be 6x. Right. So this one is going to turn into 1 minus cosine 6x. Over 2. And this cosine squared is going to turn into 1 plus cosine 6x over 2 dx. It doesn't have to be, no, it could be a 2 and a 4. Yeah, it does not have to be the same. Well, I would need two of these if it was the fourth. Yeah, I would just keep doing as many as I needed, and then it would take a little bit more time if they were to the fourth, but still, that's what I would do. Okay, so the first thing that I would do is pull that 1/4 out. I'm hoping this is just a multiplication. This is 1/2. I'm thinking of this as 1/2. I really want to get that out of there just to make it a little bit easier. So 1/4 integral of 1 minus cosine 6x and 1 plus cosine 6x dx. Okay. I don't have like u substitution or something to do here. I'm just going to need to distribute. I'm going to need to FOIL and see what I have going from there. Nicely enough, When I FOIL those, since they are opposites, one minus cosine, one plus cosine, the outside inside go away. That's kind of nice. And I'm just left with 1/4 integral of 1 minus cosine squared 6x dx. Okay. Now I have just a little tiny problem here, and that is I have a cosine squared. So I'm going to have to go back to my cool little formula and use it again. I can't really integrate with the squared, so I'm going to use my formula again. So let's think about it. So now it's a 6x, and when I use the formula that has a 2x in it, what am I going to end up with? A 12x. Okay, it's a 12x. We just keep multiplying those. So I'm going to end up with, it's going to equal 1/4 integral of 1 minus, going to insert my formula in here. That's going to be 1 plus cosine 12x over 2 dx. Okay, finally, after lots of manipulation, we're ready to integrate. I'm going to think of this as a 1/2. I'm going to integrate these separately and just think of this as a 1/2. And you could rewrite this as, and it kind of helped me, I'll just go ahead and rewrite it that way. I pulled the 1/2 in front of this term just so I could kind of get a better picture. You certainly don't have to. This rewrite just helped me. I just pulled the 1/2 in front of it so I could get a better idea of what was going on. Alright, so here we go. And another thing, so I have 1 minus 1/2. If you recognize that, you'll have to do less antiderivatives. Doesn't matter, it's going to end up the same way. 1 minus 1/2 is just 1/2. Right? So actually, just to make my integration easier, I went ahead and did one more rewrite. So 1 minus 1/2 is 1/2. Let me finish and I'll show you. So I'm distributing this, basically I'm distributing the 1/2 and combining like terms. I distribute the 1/2 to the 1, and I get 1 minus 1/2 is 1/2, and I distribute the 1/2 to the cosine, and I get minus 1/2 cosine 12x dx. So all in an effort to try to make my integration easier, that's all. Which one? It's a minus 1/2 that I'm distributing. Yep, so it'll be minus. Okay, so now I'm ready to integrate. And I have the 4th. You can wait to apply the 4th at the end. I'm just going to jump to the end. I'm hoping that we're okay with the integration part just for time's sake. What we should end up with is 1/8 x minus 1/96 sine 12x plus c. 1/96. Okay. What? This is a minus. 1/8 x minus 1/96 sine 12x. Okay, how did I get the 96? It's the 1/2 times the 1/4 times the 1/12. Because it's a little baby u sub, the 12x. Okay? Alright, our last one. This is one where we're going to have to utilize that sum and subtraction formula, because I have noticed how my angle measures, the 5x and the 4x, are different. That's a bit of a problem. So we're going to utilize on the first page where it says, let's see, this one would be sine A cosine B. We're going to utilize that first formula on that previous page. Bless you. Okay, so I actually need a little bit of a room. Is everybody okay with this last one that we did? Okay. Actually, I'll just reserve it. We'll just go up. Okay. So we're going to utilize, and I'll write the formula up here for you. Of course, I'm not going to be giving you the formulas. This is the formula from the previous page. And this will allow us to integrate this crazy looking thing. Okay, so I'm going to use this formula. I'm going to use this formula to change the way this looks. Okay, so I have integral of, my formula says there's a half, so I'm just going to put the half out there. Then I have sine A minus B. So this would be my A, and that would be my B. So A minus B, 5x minus 4x is just x. So I have sine x. Okay? Then I have sine A plus B. Again, this is a formula. I'm just using a formula. Okay, you'd have to know the formula to be able to do this. Sine A plus B. So 5x plus 4x would be 9x. So this would be plus sine 9x. Okay? Now that's going to be way easier to integrate. Yeah, we'll just integrate now. So we get the integral of sine is negative cosine, so I have a half times negative cosine x. The integral of sine of 9x, that's a little baby u sub, right? Got the 9, it's 1/9. And actually it's a minus, right? It's minus 1/9 cosine 9x. Okay, plus c, and then we clean it up. So I have negative 1/2 cosine x minus 1/18 cosine 9x plus c. Okay? How are we doing? Is that okay? I tried to show you one of each of those kinds. Okay, great.